Hi everyone, I'm Dan Fullerton, and today I'd like to talk to you about conductors. Our objectives are going to be to understand the nature of electric fields and electric potential in and around conductors, to explain the mechanics responsible for the absence of the electric field inside a conductor, and know that all excess charge must reside on the surface of the conductor, explain why a conductor must be at equal potential, and apply this principle to analyze what happens when we connect a couple conductors by wires. We want to graph the electric field and electric potential both inside and outside a charged conducting sphere. And finally, understand induced charge and electrostatic shielding. So let's dive right in. Charges in a conductor. Charges are free to move in conductors. At electrostatic equilibrium, there are no moving charges in a conductor, therefore there's no net force. And the electric field inside the conductor must be zero. Gauss's law also states that the charge enclosed must be zero. So all excess charge on a conductor lies on the surface of the conductor. The field on the surface of the conductor must be perpendicular to the surface, otherwise those charges would be in motion. So electric field inside a conductor, zero. All the charge lies on the surface of the conductor, and the electric field runs perpendicular to the surface of that conductor. Let's take a look at the electric field on the surface of a conductor. If we focus on just the outer surface of a conductor, we'll take a look at the integral over the closed surface of E dot dA, Gauss's law, which we know must be the total enclosed charge divided by the permittivity of free space, epsilon 0. And then we can state, by symmetry, we know that the charge must be sigma A. And if symmetry exists, we can use this to find the left-hand side here is just going to become the electric field times the area equal to, well, Q is sigma A over epsilon 0. Oh, look, we can make a ratio of 1 with our A's, divide both sides by A, and state that the electric field is sigma over epsilon 0. Should make sense. You have the largest electric field where you have the highest surface charge density. Let's take a look at charge distribution in a hollow conductor. In a hollow conductor, you can determine the location of charge by utilizing Gauss's law. Let's choose a Gaussian surface in the middle of the hollow conductor, making note that the electric field inside the conductor must be zero. So if we choose that as our Gaussian surface, then Gauss's law states that the integral over the closed surface of E dot dA must be our total charge enclosed divided by epsilon 0 again. However, if the electric field is zero inside the conductor, which is where we've chosen to draw our Gaussian surface, if E equals 0, then we can show that the charge enclosed must be 0. Therefore, the charge must remain on the outer surface. The entire conductor is at equipotential, and field lines must run perpendicular to the conducting surface. Let's take a look at what happens when we have conducting spheres connected by a wire. Two conducting spheres, A and B, are connected by this wire. Sphere A has a radius of 5 centimeters and sphere B is 20 centimeters. A charge of 200 nanocoulombs, Q, is placed on sphere A while sphere B is uncharged. Then we connect them by that wire. Find the charge on each sphere after the wires are connected. Well, once connected by a wire, we know that these have to be at equipotential. Further, we know that the sum of QA and QB must be our total charge, Q. So total charge, Q, is QA plus QB. And therefore, we could say that the charge on B is equal to Q minus QA. And as we mentioned before, we also know that the potential at A must be equal to the potential at B. Well, with that, let's see if we can't figure out what the charge is on A and B. To begin with, let's start by writing that the potential on A is going to be equal to QA over 4 pi epsilon 0 RA. And that must be equal to the potential on B, which must be QB, charge on B, divided by 4 pi epsilon naught RB. All right, a couple simplifications we can make there. 4 pi epsilon naught we can divide out on both sides, and therefore state that QA over RA must equal QB over RB. All right, a little bit more rearrangement. If QB is Q minus QA, then I could write that this must be Q minus QA over RB, which implies then cross multiplication QARB must be equal to Q times RA minus QA RA, just distributing that RA through. All right, a little bit more algebra here. We could say that QA RB plus QA RA equals Q RA, or solving for QA, the charge on A must equal Q RA over RA plus RB. Now we can substitute in our values. If Q is 200 nanocoulombs, RA is 5 centimeters, RA plus RB, that's 5 centimeters plus 20 centimeters, or 25 centimeters. What I'm going to come up with is a charge of 40 nanocoulombs is my charge on QA. Well, then what's QB? QB, if you recall, we said is Q minus QA, which is going to be our total charge Q, 200 nanocoulombs, minus QA, 40 nanocoulombs, or 160 nanocoulombs. So we've found the charge on each of those spheres. Again, once they're connected by a wire, they're at equipotential. All right, let's find the electric field and the potential due to a conducting sphere. Here's our sphere down here. Graph the electric field and the electric potential both inside and outside this solid conducting sphere. Well, right away we know the electric field inside the conductor must be 0, so let's fill that in up here on our electric field. Inside the conductor, where the magnitude of the R is less than the radius of our sphere, let's draw that in here. That's capital R, the radius of our sphere. And outside that, we've already done this many, many times. We know that we have this sort of shape where it's Q over 4 pi epsilon naught R squared. And that point there is sigma over epsilon naught. And at that point, the electric field, of course, is perpendicular to the surface. Electric field, sigma over epsilon naught, and then it falls off as Q over 4 pi epsilon naught R squared. And the other side, of course, symmetric. Now the potential inside the sphere, just a little bit different. Inside the sphere, we must be at equipotential. We're connected. We're all in a conductor. So we have a constant potential inside the sphere, Q over 4 pi epsilon naught capital R, and outside of that we fall off as Q over 4 pi epsilon naught R, as opposed to R squared for the electric field. Not the prettiest graph in the world, but I think you get the idea of the general shape. All right, before we move on, one other interesting fact. Let's talk about a Faraday cage. Any hollow conductor has 0 electric field in its interior. This allows for hollow conductors to be utilized to isolate regions completely from electric fields. In this configuration, a hollow conductor is known as a Faraday cage. And sometimes you can see this effect if you step into an all-metal elevator. Oftentimes, if it's an all-metal elevator completely enclosed, your cell phone's not going to work anymore. You've been isolated by those electromagnetic fields. Hopefully this gets you started with conductors. If you need more help looking for more information, check out aplusphysics.com. Thanks, and make it a great day.